I'm Sa.
I'm Sahil.
And today we're going to be demonstrating our project, the Smart Personal Rapid Transit System by Quantum Locking and Superconductivity, by showing the superconductivity part of our project, which we'll be doing. So Sahil, would you like to explain our setup?
So this is a superconductor that we have right here. It's yttrium barium copper oxide. It's a type 2 superconductor, which means that it works at higher temperatures relative to other superconductors. It actually works at, its critical temperature is negative 322 degrees Fahrenheit, or 77 degrees Kelvin. And that is a lot higher than any other current superconductor that we have. It's also, essentially, it's a sapphire wafer, and it's coated with 1 micron of yttrium barium copper oxide. And essentially, it's a ceramic material, so when we put it around this magnet, it doesn't do anything. It's not affected by the magnetic field at room temperature. But when we cool it down to its critical temperature, that's when it's going to start being affected by the magnetic field.
Yep, and over here we just have our old superconductor, which was just the ceramic material, which wasn't coated by the sapphire, and it did not work very well in our first trial. So today we're going to be using the new one.
Exactly. So essentially we're going to be starting with the Meissner effect as well as magnetic flux pinning. These are two different effects that together create our project and create the more effective way that our project works than traditional maglevs.
Okay, so
let's get the liquid nitrogen.
Yep. And I'm going to move back our seats for safety reasons.
Yes, we don't want anything spilling. It is extremely cold, and we do want to make sure we're safe.
So now that we got our liquid nitrogen, we're going to demonstrate the experiment. So
we've prepared our superconductor by wrapping it in saran wrap so that it's insulated, and so that the liquid nitrogen actually has like a place to cool it down. If you want to put.
Oh, yep. Now we are going to put this. We're going to be using this as a spacer, so it can demonstrate both the Meissner effect and flux pinning over here.
So the Meissner effect happens when the superconductor is cooled in the. The magnetic flux pinning occurs when the superconductor is cooled in the presence of the magnetic field, while the Meissner effect can happen only in the presence of the superconductor. Look at that. Okay. So now that the spacer is ready, we're going to be demonstrating something called the magnetic flux pinning and the Meissner effect. The Meissner effect happens when the superconductor is cooled down to its critical temperature and placed in the magnetic field. But magnetic flux pinning can only occur if the superconductor is cooled in the presence of the magnetic field. So here we're going to be demonstrating that.
Okay, so as a precaution, we're going to be moving our seats back.
Exactly.
So we don't get any liquid nitrogen on.
We'll be pouring the liquid nitrogen now.
And as you can see, this is extremely cold. It's boiling at room temperature. So that just gives you, that just shows you how cold it really is.
Exactly. And so we're going to be waiting until the superconductor is cold enough that the liquid nitrogen is not going to be boiling. And that shows that the superconductor has reached the temperature of liquid nitrogen.
Okay, so
we just added some more liquid nitrogen. I think it is ready now, so
we will
just wait for it to boil a little bit more.
The spacer from it.
Okay, ready? Again, move back a little bit.
Yep. And the spacer has some liquid nitrogen in it, so I'm going to be extremely cautious.
Just make that fix a little later. So as you can see here, it is actually levitating over the magnetic field. So let's add a little bit more liquid nitrogen.
And here it's demonstrating magnetic flux pinning and the Meissner effect, as you can see.
Ooh, careful.
And that was cold. And it is locked in place now. And you can move it around here, and it's extremely hard to move on the magnetic axis because it is both demonstrating both effects that we mentioned. And do you want to put a little more liquid nitrogen?
Yes. Let's also demonstrate the rotational part.
Yep. And just one more thing over here, you can see that it is levitating extremely high for a.
Let's actually show it this angle. This angle, you can see it's actually quite high compared to any other traditional maglev system.
Yep. And it doesn't matter what goes underneath it. If you put anything underneath it, nothing will happen to the superconductivity. So that hat holds great benefits for bad weather conditions such as snow. It can just levitate over the snow.
Exactly. So here we're going to be showing a very interesting property. Essentially, when we put it into a rotational magnet, what happens is it can actually spin freely because the magnetic field is the same around the entire axis. So essentially, what we're going to do is have a linear magnetic field that the axis will go in a linear fashion.
Mm-hmm.
That will allow the superconductor to actually travel on that while it's locked. And in that case, it'll essentially be extremely stable. It'll be locked in place, meaning that it won't be able to move out of the field.
Exactly.
And that makes it a lot better than traditional maglev systems, which need a lot of computational power to keep the vehicle at the correct distance between the track.
And one good thing about using the superconductor is that, I'll actually put it over here, because it's some more of the next on next. It doesn't matter how you hold the superconductor because anyway, it's still going to stay locked into the field. So it's not exactly levitating, but it's locked in the air. And we'll actually demonstrate that to you and by, I think there's still a little nitrogen. Okay, we'll be demonstrating that by showing you that even if we rotate it around, so I'll show that again. You can hold it like this. And you can even
upside down.
Put it even upside down. And it will still demonstrate the superconductive properties.
So essentially what's happening is there is the fluxons that are surrounding the superconductor. Because superconductors exhibit this property, which is called the Meissner effect, and essentially what happens is they expel all the magnetic fields from within them. And the fluxons have to go around the superconductor in order to be able to exhibit this property. And what happens is it's essentially surrounded in magnetic fields. Mm-hmm. Just like how a ping pong ball over a hairdryer will levitate over the ground, this thing will also be able to levitate in the magnetic field.